Hi, folks. This is Stan Forrester. I'm your instructor for Physics 203 and 204. We're talking about electromagnetic inductance. In particular, I'm going to run you through a solenoid type problem. Okay, and so we're going to actually do several different types of problems. Hopefully, we can cover most of the ground that you're going to encounter. Okay, so here let's read off the situation. Here's our illustration. We have current entering from the left. We have a loop of wire that goes round and round and round and round. That's the definition of our solenoid. And it continues off to the right. Okay, we have some diameter that we'll give you in a few moments and a length that we'll give you in a few moments. Okay, now if we take our thumb and run it, well, okay, so the camera has it. The camera has my view reversed. Okay, so I'm not going to hold my hand up for this, my right hand up for this. Okay, so, but if you take your right hand and point the thumb, maybe I can do it with my left hand. Okay, yeah, the camera's got it all reversed. I'm not going to mess you up that way. Point your thumb along the direction of the current and then curl your fingers around. You can see that um, on the left, the magnetic field due to that wire is going to come out of the page above the wire and into the page below the wire. But now when we transfer to the coil itself, you have to change direction. This is initially going to be headed upwards. Okay, and when you curl your fingers, you're going to see that that magnetic field is going to go into the coil. It's going to go into the coil. And that's just going to continue for each of those loops. They're going to build up and make some net magnetic field that is fairly constant inside the coil. So that's the theory behind it. Okay, so here's the problem. A 0.14 amp current in a conducting wire is wrapped into a parallel coils, also called a solenoid. It creates a reinforced B field inside as shown. Consider the case with 200 coils forming a 0.75 centimeter diameter cylinder with a length of 5.95 centimeters. The assumption here is that the length of the cylinder is a constant magnetic field. We're assuming a constant magnetic field inside the solenoid. That's pretty standard for solenoid problems. Okay. The inductor has an iron core, which is not shown, and increases the effective magnetic permeability by a factor of 4,000. In other words, we're going to take that factor mu naught that we've been using, and we're going to multiply it by a factor of 4,000. Okay, so what is the B field generated inside the solenoid? Okay, so here we go. Here's our key idea, magnetic field inside a solenoid. We've already gotten this down to possibly one or two equations. We just have to figure out what it is from the stock of data we're given. We're given the number of turns, we're given the current, we're given the length of the solenoid. Okay, I did something odd before. I got the current wrong when I was working out the details. And yes, I have the right current there. Okay, 0.14 amps. It always goes back. It's always good to go back and check. The length of your solenoid, 5.95 centimeters. Notice that I've noted it down in your standard SI unit meters. Okay, because everything, when we plug these things into these formulas, we don't want to plug 5.95 centimeters in there. We want to plug in something in the units of meters. Okay, effective permeability. Well, that's going to be your 4 pi times 10 to the minus 7th Tesla meters per amp. Okay, but since it's iron, we're going to multiply that by 4,000. Okay, iron is just simply has a much better magnetic permeability than nothing. I guess you could say it's better than nothing. Okay. So here's your equation for the solenoid. Okay, if you go look in the chapter summary, I'm pretty sure this is one of your numbered equations in your textbook. So the magnetic field due to a solenoid, an air solenoid, would be equals mu naught. That's that magnetic permeability of vacuum times the number density, the turn density of the coil, not the number of coils, the turn density times the current itself. Okay, as we go ahead and expand this turn density, we have mu naught times the number of turns in the coil divided by the length of the coil times the current. Okay, and notice that I have not gone ahead and put in 4,000 times this. Okay, solve. Not applicable. The base equation, which appears in most of our textbooks, okay, that's one of those ones that you would start with. The equation that you start with is the one you're actually going to calculate with. So for under solve, we just put down not applicable. Okay, let's substitute in some numerical data. Okay, here's your magnetic permeability. Here's the vacuum magnetic permeability, but we're going to multiply that by 4,000. Okay, here's our turn density, 200 divided by, not by 5.95 centimeters, but 0.0595 meters. Okay, and here's our, there it is. I did it again. Watch that. See that? 0.14 amps. And that's going to come out to be 2.366 Tesla or 2.37 Tesla. Yeah, I had corrected that, the actual final answer before, but I didn't catch the current. What's the value of the solenoid's inductance? Okay, the idea is going to remain the same, but we're going to back up to the process, the whole stock of data, and we're going to add a few items. Okay, we're going to need the inductance, and I put the question marks there. And did I put magnetic field with question marks up here? I did not. All right, so you can deduct a few points from me if you want to do that. Okay, R is the radius, which is half the diameter, 0.75 centimeters divided by 2, so it's 0.375 centimeters. You convert that to meters, 0.00375 meters. And we're going to need the cross-sectional area of the solenoid. That's just pi r squared. We're going to plug 3.1415 times the square of the radius that we just came up with, and we're going to come up with 4.419 times 10 to the minus 5 meters squared. Okay, we're going to identify our equation. This is the equation for the inductance of a solenoid. Again, this is probably something you're going to find in the chapter summary of your textbook. And the inductance is the magnetic permeability times the square of the number of turns times the area divided by the length of the coil itself. Let's substitute in some numerical data. Going to do a little magic with your calculator, and you're going to come up with 0.1492 henries, which we're going to just notice that what we're putting in here. What's the smallest? Well, 200. That's a number. That's exact precision. Okay, so let's see. So we would probably round this off to 3 digits because your length of your coil is only given to 3 significant digits. But if we round it off to 3 significant digits, 0.149 2 4 9, and I'm going to drop that 2 there because that's an extraneous digit. That's, if we put that in there, we'd be claiming precision that is not warranted by the data that we put in. Okay, if the current has a constant value, what is the EMF generated across the solenoid? This one's a distractor. EMF is going to be proportional to the rate of change of the magnetic field. Matter of fact, I'm going to run forward here a little bit. Okay, here we go. We have the rate of change of the magnetic field. That's going to be proportional to the electromotive force. Current's constant. The magnetic field is not changing. There is no EMF being generated at this moment. Okay, no current, no, and the next one, which is more positive, no current, no potential, so there is no positive or negative. It's another distractor. If the current is increasing at a rate of 4.2 amps per second, what is the rate of the B field changing? Well, basically what we're going to do is go back and use the first equation we did. The magnetic field is equal to our magnetic permeability times our turn density times the current, and we're going to put a rate of change in there. So the B becomes delta B over delta T, I becomes delta I over delta T. They give you the rate of change of the current. So let's go ahead and let's just put those in. Okay, so here's this 4.2 amps per second. And here's a few other things that we calculated out before. This is your turn density. That's 200 divided by the length of the coil itself. And this is 4,000 times 4 pi times 10 to the minus 7th. Okay, so we'll go ahead and we'll crunch these numbers here, and we're going to end up with about 680 Tesla per second. 680 Tesla per second. Sorry, I almost said just left off the per second. Okay, what's the magnitude of the EMF generated across the solenoid? Well, here we have, oh my God, can I make this bigger? There we go. Okay, so the EMF generated is just going to be Faraday's law. It's going to be minus, that's the negative sign, that's the Lenz's law portion of this, that this EMF is going to oppose the changes, okay? So it's going to be your number of turns divided by the, times the cross-sectional area times this rate of change of the magnetic field, which we just calculated. Let's go ahead and substitute some data. Okay, that should be the same color as all of this stuff. Okay, substitute data looks like the following. Here we go. Okay, again, we're not really concerned with the negative side. We're concerned, what is the electromotive force? So let's go ahead and throw some absolute value bars around that EMF, and let's go ahead and calculate this out. Not sure why that didn't show up the way it was supposed to. And this is going to be 5.998 volts. Again, we have to round this off to 3 digits, and we're going to end up with 6.00 volts. Now, I could put down 6 volts, but that doesn't really tell us much about how many significant digits we have. 6.00 implies that those last 2 digits are significant. Which end of the solenoid is more positive? This one's a distractor. We look at the thing, okay, current's going in this side. Okay, this has the more positive electrical potential. That's where it goes in. This one has the more negative. That's why it flows in this direction. Okay, so there's nothing complicated about that one. That was a little bit of a distractor. Okay, that should clear it all up. If you have any questions, please post those.